Hey everybody, Steve Sefcik from Should Have Been Engineering. I thought we'd do something a little bit different today, and we're going to look at how a clutch works, how a slipper clutch works, and also how the star springs function. So this is going to be germane to the ZG1000 and the ZG14. The parts are a little bit different obviously between them, but the function is exactly the same. This is a ZG1000 clutch that we're going to be working with, but trust me, everything translates over to the 14 just fine. So let's go ahead. I'm going to move in so we can set up our shot so you can see down in here. I'm going to assemble the clutch and show you how things work, and then we're going to move on to how a slipper particularly works. Okay, so here we have the clutch basket. This is the primary gear. This interfaces with the crankshaft. So when the crankshaft is rotating one direction, this is going to be rotating the opposite direction. The purpose of the clutch is to transmit the power from the crankshaft into the input shaft of the transmission, okay? And so, as you can see, the clutch basket would be turning, okay? Now, let's go ahead and start assembling the clutch. We're going to leave some parts out, but you're going to get the basic idea. This is the inner hub of the clutch right here, okay? The inner hub goes in, and what the inner hub is doing is it's actually connecting. Let me take these star springs out of the way. The inner hub is actually connected to the input shaft of the transmission. So the output shaft of the clutch basket can turn, and the input shaft can stay not turning at all, okay? There's nothing to connect them right now. This is where our clutch stack comes in, okay? So in the way a clutch stack will go together, you would have a friction plate, and then you would have a steel. And then you build this stack just like that. Now if you notice, the friction plate interfaces with the clutch basket. The steel is interfacing with the inner hub. So when the clutch basket is turning, the friction plates are turning. And when the inner hub is turning, the steels are turning, okay? And by the way, this is what's called, when you put all these together, this is what's called our stack height. We're going to come back to that. Now, think of it this way. I've put all these in. I've got my clutch stack fully built. This is the pressure plate. But underneath the pressure plate, in this case, we have star springs. And they go on right here, and as you see, they're interfacing into this clutch hub, okay? Now, with a regular clutch, you do not have star springs. And with a regular clutch, this inner clutch hub is one piece. With a slipper clutch, it's two pieces. Now, here's what happens with a slipper clutch. A slipper, also known as Kawasaki calls it as a back torque limiting clutch, has the ability to basically disconnect the clutch when you're on a hard downshift. And the way that that's working is when the inner hub is turning faster than the outer hub, there's a built-in mechanical ability for this to separate and lift and push up on the pressure plate. I know this gets a little bit confusing, so you're going to have to follow along with me on this. Let's show you how that works. Okay. This would be basically what a regular clutch inner hub would be like. You know, probably one piece, machined out of one piece, or a couple pieces bolted together, all right? This is different in that it's two pieces. And what you have here is, on the base piece, and I know that this is going to be very hard to pick up, but here you have these three ramps. These are like receivers. On one side, it's 90 degrees. On the other side, it's probably about 45 degrees. We also have these pegs, and they also are flat on one side, 90 degrees, and about 45 on the other. Here's how it goes together. Those pegs fit into those little receivers, just like that. Now watch what happens. When I try to push the inner hub in the direction that the flat sides are on, like this is the same as if we were driving this from the outside, from the clutch basket. Okay? You can see everything turns together. But now what if the power came from the inside and it came on the steels through the input shaft? In other words, we've downshifted and our rear wheel is spinning the input shaft faster than the crankshaft is turning. Well, this is what happens. This inner hub, see how that's lifting? That inner hub starts climbing those 45-degree ramps. See how that inner hub is climbing? Okay, now, this is where the whole slipper clutch comes in. This is what your star springs do. They retain that. They hold that down, okay? So there's that big nut, all that's held down on there, and then here's your pressure plate, okay? Pressure plate sits down over the top of it, and then of course you have your springs, okay? Now, remember, if you've got your stack height here, your frictions and your steels, they're being squeezed right now by the pressure plate. All of a sudden, you get back torque applied. Look what it does. See how that worked? You see what it did? Is it lifted the pressure plate. When it lifts the pressure plate, it's just like as if you lifted the pressure plate by applying the clutch. When you lift that, it takes the pressure off the stack. When you take the pressure off the stack, you've relieved the pressure and you've effectively separated the crank and the input shaft of the transmission. Now, the star springs. These are known for braking. They'll usually fracture someplace along in here. When the star springs fracture, now all of a sudden you have these loose pieces of metal that can get out, they'll fly around, and they'll get inside of the clutch stack. You got a piece of metal inside of here someplace, your clutch is going to start slipping, you're going to start tearing up your clutch, okay? So when you start seeing problems, particularly, let's say that you can feel in your lever, when you grab a hold of the lever, you feel like a bump, 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 bump. That's your clutch discs kind of skipping over this broken piece of metal that's come off when you have a star spring failure. Also, the nut that retains the star spring, if you notice this is a crimped nut. It kind of is dinged in on one side, so basically it's designed for one use. You tighten this down one time, next time when you go to replace your star springs, you replace the nut also. The C14 uses 4 star springs. The 10 uses 2 star springs. The later model ones do. And if you have an older one, you should upgrade to the 2 star spring. They went from 1 star spring to the 2 star springs around 97 or 98. So if you have an earlier model, you can upgrade that. Now, let me show you one thing that has an awful lot to do with what happens when you get an aftermarket clutch. Let's go back to what we were talking about here, stack height. Stack height being the full thickness of our frictions and our steels. Now you can see these are, out of order, as if we had them in the clutch, but that is the full stack height, okay? Your stack height has a measurement that has to be balanced, and basically what it's doing is balancing the pressure of the pressure plate versus the star springs. So the hold down springs that you have for the pressure plate, if you were to, let's say, buy aftermarket, and these were very strong. Well, now what's going to happen is, when back torque is applied, you can't really overcome these very strong aftermarket springs, so you're going to have very limited usefulness from your back torque, from your slipper clutch. It's just not going to be able to lift up very much to separate the clutch and let the clutch freewheel. Conversely, on stack height, this is actually how you tune what your slipper function is. If your stack height, if you want more slipper function, you want the slipper to come in earlier, you use thinner steels. These steels are measured, and they come in basically about 2 millimeter thickness, 2.3, 2.5, 2.0. And the thickness that you select for the total amount of your steels is what affects your stack height. A low stack height would allow the slipper to actually engage very early. In other words, it wouldn't take a whole lot of effort for the inner hub to start climbing and pushing the pressure plate off, okay? On the other hand, a high stack height would mean that this really had to climb quite a bit before it started lifting the pressure plate. So hopefully you can understand that when you're dealing with the pressure going on inside of a slipper clutch, you kind of have this balance of pressures from the star springs, the inner hub retaining spring, the pressure plate springs, and how much height you have in the stack. All of those are going to influence how your slipper works, whether or not it will come on and slip very easily on a very easy downshift, or whether or not it's going to come on and slip. It's going to take a whole lot more back torque in order to get it to slip. All right, everyone, I hope that kind of demystified how the back torque limiting or slipper clutch actually functions, how it actually is causing the clutch to slip for us when we're on downshifts. I can also tell you from personal experience, I tried a non-slipper clutch in my Concours, and I figured out pretty quick that with the drive shaft, I'd probably kill myself if I went to the mountains without a back torque or a slipper clutch. So I went back to the stock slipper. It's one of the few parts in my bike I think that is absolutely stock and is better than anything I could have ever hoped to come up with. It's absolutely a great, ingenious, and very simple way of approaching getting the clutch to slip for you on your downshifts or when your rear wheel is going faster than your crankshaft. So, all right, I appreciate everybody coming to watch. Catch me at Should Have Been Engineering. As always, if you own a Concours, a 1000 or a 1400, join COG.